Hello, everyone. It's a great honor to be here to present our work, the MagX, which is the Untethered mobile hand tracking platform with passive magnets. It is a joint work between Shanghai Jiao Tong University and the University of Michigan Ann Arbor. My name is Mingke Wang, and I'll be the presenter today. So, as we all know, the hand is one of the most expressive parts of our body, and it helps us to interact with the physical world. By unlocking and understanding the variable semantic information encoded by this hand movement, we can enable a lot of useful applications. Driven by this motivation, there has a lot of solutions coming from either the academia or the industry. For example, Nintendo has bring out the Power Gloves back in the 1980s. By wearing these heavy gloves, the user can have a more immersive gaming experience. And in recent years, due to the rapid development of VR and AR devices, we now have the Oculus and also the Ultra Leap. From the algorithm point of view, we can find a lot of online open source solutions on hand tracking based on machine learning or deep learning. They usually use the RGB camera or the depth camera. Besides, we also have the radio frequency-based solutions. It decodes the information stored in the reflected wave to conduct hand tracking. Furthermore, hand tracking can also support health applications. For example, monitor our hand movement during our daily life can help us identify and detect unhealthy behaviors. For example, the face touching or rubbing nose and eyes. These unhealthy behaviors can increase the risk of getting diseases like COVID, and also they may introduce infections and allergies. So here are some representative tracking methods. For example, the camera-based, the radio frequency-based, and also the IMU-based. Starting from the vision-based solution, they have high accuracy, long sensing range, but the problem is it is not resilient to line of sight obstructions, which means that if there is any obstruction between the camera and our hands, the system simply does not work. And also the camera-based method does not work in low light. The radio frequency-based method share the same problem. The IMU-based method uses the motion sensor to detect the human's movement. The motion sensors are usually accelerometer and gyroscopes. In order to capture the static or the absolute position of our hands, these methods usually have to integrate their data over a period of time, which will induce the accumulative error. So in this project, we want to explore the possibilities of using magnetic tracking. The magnetic tracking is inherently resilient to line of sight obstruction. That's because the magnetic field will pass through the common material, for example, the human body, the woods, the plastic, etc. And also the magnetic tracking can have high accuracy within the sensing range. It is also privacy preserving and has low power consumption. So now let me introduce our platform, the MagX. In a word, the MagX is a fully untethered on-body tracking system utilizing the passive magnet and a novel magnetic sensing platform. As you can see from the first row, it is our design sensing platform. The design is carried out by our simulation-based designing pipeline. We have 2 layers and 8 magnetometers in total. This 2-layer design is able to capture more diverse magnetic field data to increase our accuracy. On the lower row is our magnet. We came in 3 different form factors, which is the wristband, the ring, and also the small ring. Noted that these are passive magnets, so they does not require any maintenance, and also it does not require batteries. So our system works by first, the user will wear the passive magnet on their fingers or wrist, and then it will put on the sensing unit on their body. The sensing unit will continuously gathering the data from the magnetometers. These data will then be transmitted wirelessly to the processing unit using Bluetooth. The processing unit will then denoise the data and initiate the tracking process. We use an analytical model to conduct the tracking process, which means it is training-free and is power efficient. We implemented our algorithms on Raspberry Pi and smartphones. Based on the tracking result, we can extract semantic information and provide valuable feedback to our users. So here, let me introduce the theoretical basis for our magnetic tracking. So the model is called the dipole model. The dipole model is used to describe the magnetic field distribution around a spherical magnet. The variable R here is the relative position between the magnet and the observation point. The variable M here is called the magnetic moment, which encode two information. The first is the strength of the magnet, and the second is the orientation of the magnet. Please note that the magnitude of this field is the grades with the distance at the power of 3. The sensor reading can be then modeled as the linear combination of each magnetic field and also the background magnetic field, which is usually the Earth's magnetic field. The index I here is the sensor index. The index J here is the J's magnet. So our system can leverage multiple magnetometers to conduct tracking of multiple magnets. The tracking process can be modeled as the least square error optimization problem. By minimizing the error between the observed sensor reading and the calculated sensor reading, and find the best combination of orientation and position, we are able to track the magnets. This problem can be solved by using nonlinear solvers, such as the LM algorithms. For the ground truth collection, we did not use the famous RoCap system because it is too expensive. Instead, we're using a leap motion-based platform. The leap motion can track the pen-shaped tools at the accuracy within 2.5 millimeters, and it costs lower than $200. We 3D printed the pen-shaped tool and placed our magnet inside this tool. By tracking the position and rotation of this pen-shaped tool, we are able to get the ground truth for our magnet. Our MagX system can track 5 degrees of freedom for each magnet. And here is some performance evaluation. First, for the position arrow, MagX can achieve millimeter accuracy within about 25 centimeters. For the orientation arrow, please refer to the plot on the right. Because MagX is a mobile system, it is really important to evaluate the power consumption. For the sensor array, the MagX incurs 0.22 watts power drain, which can be translated into 8 hours usage on a small battery pack, about 500 million hours. For the mobile device, which is our computing unit, we measure the power consumption on the Raspberry Pi and also the Raspberry Pi Zero. Our power drain can be as low as 0.16 watts. Based on this magnet tracking result, we can build a model to use this highly semantic information to enable more useful applications. For example, the AR interaction use case, where our user will wear this MagX system on his wrist and attach magnet to each fingers. The MagX system can be able to detect different gestures. For example, the neutral, the click, the finger heart, the stop sign. Besides, our MagX system can also conduct face touching detection. We came with 2 different form factors. The user can either place the sensing platform on their hat or just wear it as a pendant. The magnet can be worn as the ring or the wristband. Here is our tracking trajectory and also the classification confusion matrix. Our MagX system can achieve over 92% F1 accuracy. Here is some demo videos on face touching detection and the AR interaction. Both these demo videos are run in real time, And as we can see here, our MagX system can be able to track the face touching on different face areas, and also can monitor the hand gesture quite accurately. And yes, our MagX also comes with different form factors. We have already introduced our the ring form factor and also the wristband form factor. But indeed, our MagX system can also track very tiny magnet with about 4 millimeter in diameter. And this will enable us for more applications. For example, there is an emerging technology called the capsule endoscopy, where the patient will swallow one of these tiny capsule to know what is going on inside their bodies. It will be very helpful to know the position of these capsules inside their bodies, and that's when our MagX system can come in handy. In our experiment, we place a very tiny magnet in the middle of the box and cover it using a 6.3 centimeter pork belly. By using our MagX system, we can accurately locate this tiny magnet and to know its presence. For more details, please refer to our demo videos, which is the QR code showing here. And yes, our MagX system is an open source project. You can find all of the hardware design, the pipeline, and the tracking algorithm online. In conclusion, our MagX system is an untethered and fully mobile hand tracking system. It uses the novel magnetic sensing scheme to achieve high accuracy hand tracking. Our future direction will include addressing the environmental disturbance and also redesign the form factor to have a better usabilities. We hope our project can lay the foundation for more interesting magnetic-based tracking applications. And that's all. Thank you for your attention.